All right, the wonderful pH calculations. So it's derived from a French word. On the count of three, let's say this word together. 1, 2, 3. Just kidding, I don't know how to say it either. So if you know how to pronounce that, go ahead, knock yourself out. But it means the power of hydrogen. So pH really just stands for the power of hydrogen. And there's a couple calculations or equations that go into this. So pH, the power, and anytime you see, here's a hint, this will help you out throughout the rest of the year. Anytime you see this lowercase p next to something, it always means the same thing. That little lowercase p stands for the negative log. So we're going to see that lowercase p a couple other times, POH, PKA, other similar things, and all that means is negative log of whatever's next to it. In this case, it's negative log of H, and so it would be the negative log of the H plus concentration. Now, be careful that on your calculators you're using the log button, not the ln button. It's not the same as natural log here. So if we wanted to throw this down real quick and we had a jug of HCl, and its concentration was, let's say it is 1 times 10 to the negative 4th molar. Okay, so a fairly dilute solution of HCl. And remember, since HCl is a strong acid, that means by default the concentration of H plus in that solution is also going to be that same number. So then we would take the negative log of 1 times 10 to the negative 4th, which, if you're following along at home, is 4. So the pH of that particular solution would be 4. So that would be an acidic solution. If we want to take a look real quick at the pH scale, so you guys have seen this since middle school, but here it is again. 7 is neutral on the pH scale, right there in the middle, and that would match up with things like pure water. So pure water in a sealed container. If you have an open container of water, there's actually going to be carbon dioxide that dissolves in there, which is going to create carbonic acid, which makes it slightly acidic. And we learned about partial pressures with Henry's law. That's why the CO2 dissolves in there. As you go up on the scale, it becomes more and more basic, and so a pH scale of 14 would be like 1 molar sodium hydroxide. A couple other basic things, ammonia, oceans. Here we have coffee is going down towards the acidic side. So once we drop below that 7, we get acidic and more acidic until 0.1 molar HCl. Here is a fact. The scale does not stop at 1 and it does not stop at 14. You can go beyond both of those. That's just generally what we write it ending at. But I mean, the concentration of pure HCl is 12 molar, and so that's going to go well beyond 1. It's going to get down into the negative range. And if you get a concentration higher of sodium hydroxide, which is more than possible, the pH will go above 14. All right, back to our equation. So we already said that pH is the negative log of the concentration of H plus. But what if we're talking about a base? If we have a base, we don't really know the H plus concentration directly. Instead, we're given the OH minus concentration. And so instead, we can't calculate the pH for that, because if we take the negative log of OH, that wouldn't be the pH. That would instead be the, let me separate these two sides, the POH. So the power of hydroxide would be the negative log of the hydroxide concentrations. Well, then how do we get from POH to pH? Because who's ever heard of the POH scale? Nobody uses the POH scale. It's just a stepping stone to get to the pH scale. Here's a fact. pH plus POH always equals 14. So if you calculate the POH, you subtract that from 14, and that gives you your pH. So it's a pretty easy transition. Also, just so you know, if you wanted to get the H plus concentration from a pH, it would equal the antilog, which is 10 to the negative pH. So that's just this top equation right here rearranged to solve for the H plus. So H plus would equal 10 raised to the power of pH. And same thing with the hydroxide. That would be 10 to the negative POH. So the good news is if you're given one piece of information, you can calculate the other three. So if you're given the pH, for example, you can find the H plus concentration. You can use the pH to find the POH, which you can use to get the OH minus concentration. And so you can use kind of this round circle thing here. Real quick, going back to this pH scale, so something important to note is when we talk about something that's basic, So sodium hydroxide, 1 molar sodium hydroxide. The key is that 1 molar sodium hydroxide, it isn't that it doesn't have H+, it has more OH minus than it does H+. So if we think about this scale real quick, something that is basic, which is anything that's above 7 on the pH scale, its concentration of OH minus is greater than its concentration of H+. But because of the autoionization of water and because of the whole Bronsted-Lowry definition of acids and bases, there have to be both in the system. So basic solution will always have H+, it's just going to have less of them than it does OH minus. Something that's neutral is going to have a concentration of OH minus that's equal to its concentration of H+. And something that's acidic, so anything that's less than 7 on the pH scale, its concentration of OH minus is going to be less than its concentration of H+. So it's not about the presence of one or the other, it's about the imbalance of H pluses and OH minuses. So what that means is for those equations that I just showed you, you can transfer between any of them so you can figure out, okay, well, since there is hydroxides in this acidic system, how many is there? And you can calculate it using those. Okay, because I can hear you begging at home for some examples, let's look at the pH of pure water. So I know what you're saying, it's 7, you know that, but let's calculate it just for fun. So we're going to do it a different way than what I just showed you, and we're going to use instead kW to help us figure this out. So remember that kW is equal to 1 times 10 to the negative 14th, and we're going to say this is at 25 degrees Celsius, of course, because that's the only time that that number would line up. So kW, which is 1 times 10 to the negative 14th, is equal to the concentration of H plus times the concentration of OH minus. So since we know that for pure water those two numbers right there, the H plus and the OH minus, are going to be equal, we can say that the concentration of H plus, which is also equal to the concentration of OH minus, is going to be equal to the square root of 1 times 10 to the negative 14th. So that means in pure water the concentration of H plus as well as the concentration of OH minus is going to be 1 times 10 to the negative 7th. And if we take the negative log of 1 times 10 to the negative 7th, we would see that the pH is equal to 7, which is neutral. We've just proven it. Okay, let's say we have a solution, we find its pH, and we find out it's 5.63. Let's figure out what the concentration of H plus is in that solution. So since the pH is equal to the negative log of the concentration of H plus, we've already shown that the concentration of H plus is equal to 10 raised to the negative pH. The pH in this case is 5.63, so it'll be 10 raised to the power of negative 5.63. A hint, this negative value is really important. When you're doing the log to figure out the pH, if you forget the negative in front of the log, you'll just get a negative pH, and that's an easy fix. But if you do 10 raised to the positive 5.63, you're going to get a completely whacked out number. So make sure you put that negative in there. So if we type this in, 10 raised to the negative 5.63, we'll find out that the concentration of H plus in this solution is going to be 2.3 times 10 to the negative 6th. And that's molarity because of those little brackets right there. Alright, let's do another one. So find the pH of a 2.5 molar, so that's pretty concentrated, hydrochloric acid solution. So I can hear your question right now, well, how many H pluses is there in this 2.5 molar HCl solution? Well, remember, HCl is a strong acid, so whatever the concentration on the jug is, that's going to be the concentration of the H plus. Because really, inside of that jug, there is no HCl. There's H pluses and there's Cl minuses. It's completely dissociated. It's a strong acid. So the concentration of H plus, because of that 100% dissociation, is going to be 2.5 molar. Now, you guys probably knew that, though. And then the pH is going to be equal to the negative log of the concentration of H plus. So in this case, it's 2.5. And so we would get the pH for this one as, that's right, it's negative 0.40. So remember how I told you the pH scale can go below 1, it doesn't stop there. The pH of 1 was for a hydrochloric acid solution of 1 molar. This is 2.5, so this is even more concentrated, higher number of H plus ions. All right, and that's it for pH calculations. So that just works mostly for strong acids and strong bases. To get the pHs for weak acids and weak bases, it's going to be a little bit trickier. We're going to have to throw in the Ka and Kb. We'll still use those same equations, but we can't use them directly. We have to go through some preliminary steps first, and we'll see that on further videos.